Okay, here's another good example where we're going to figure out the slope of this and use that slope to get, because the slope is the same thing as a rate of change, we can get a linear equation for it. So we can choose 2 points on the graph. Let's take this one and this one, the two that are already kind of labeled. That looks like we have 700 there and 400. So for part A, we're going to do the delta A instead of delta Y this time, divided by delta T instead of delta X. And the delta T is going to be the change in the time from 2 to 4 is 4 minus 2. And the change in the altitude from 400 to 700 is 700 minus 400. So we got this horizontal change here is 2, and this is going to be 300. So we get 300 over 2, also known as 150. And actually, I want to go back a little bit here because I haven't been using units, and I want to include units here. So how do you get the units of this number 150? Let's think about the units of A. The units of A here are given in feet. Oops. So the vertical change here we're talking about, that 300 represents 300 feet. So that 300 represents 300 feet there. And the number 2, well, the units of t, we're talking about a change of time there. The units of that number 2 should be the same as the units of the t-axis, which is minutes. So that number is going to be 2 minutes. So that should now represent 150 feet per minute. What does the slope represent here? What is it measuring? Well, I like to think of slope as how much the vertical changes every time the horizontal changes by 1. So in this case, x is time. So every 1 minute, the altitude is going to change by 100 feet. Now, to write a linear model for A in terms of t, we're going to use the same idea as we did back in 1.1, where the general form for a linear model is y equals the starting value plus a rate of change multiplied by x. Of course, in our case, that x is really t and the y is really a. And the starting value for us looks like the y coordinate of that point, meaning at t equals 0. Right when they got on the ski lift, they were at an elevation of 100. And the rate of change we just figured out is 150 feet per minute. So we can write this as A equals 100 plus, oh my gosh, I just wrote 100 instead of 150 there, excuse me. 100 plus 150 times t. Okay, so that wasn't too bad. Now, how can you check that this is really the equation for this? This is an important thing to do. If you come up with an equation for any kind of graph, you check it by making sure that the points on the graph are actually solutions. because that's what it means for this to be the graph of this equation. It means, for example, this point is 400. That means if you plug in t equals 2, a should be 400. So let's make sure that works. Is 400 equal to 100 plus 150 times 2? And you can do the math here. Make sure that works. And it does. You end up getting 400 equals 100 plus 300. And yes, it is. So yes, this really is the equation of that graph. Now, here's one more exercise for you to try. It's the same idea. I should say with these ones, you don't have to copy down the entire problem necessarily. I'm starting to realize this is a lot of stuff for you to write down by hand, and I don't want you to spend all of your time just copying as fast as you can. I'd rather you slow down and think a little bit. And it's sort of up to you. If you're the kind of person who really likes to use your notes as a reference and you like getting your notes as neat as possible because you enjoy doing that, that's great. And you want to be able to come back to it, then yeah, you should copy down all these exercises. But if you are more like me, the way I was in school, I was really bad at writing notes and listening to somebody talk at the same time, so I took down pretty minimal notes. And it's okay if for problems like this you don't write down every single thing if you don't think you're going to use it later. So anyways, but what you do need to work out the problem on your own. And good luck. It should be pretty similar to the last one.